Okay, now we want to look at some more examples, but this time we're going to include friction in our examples. Okay, this first example says you have a 15 kilogram block and it weighs 147 newtons if you multiply 15 kilograms times 9.8, and that rests on a table with an upward applied force of 40 newtons directed at an upward angle of theta equal to 60 degrees as shown. So I've got this block here, and we're going to be pulling at an angle of 60 degrees with a rope or something. And so what's going to happen? So obviously this force is going to have a vertical component and a horizontal component. The horizontal component is going to make it want to slide to the right. But if there's friction, we're going to see friction have an effect opposite to that. Now, we're given this situation. We're told that the coefficient of friction, the coefficient of kinetic friction, is 0.15, and so that implies to us that this thing is indeed going to slide to the right, and we want to find what is the acceleration of the block. Now, the first thing I would do mentally is I would make a check to make sure that this force, 40 newtons, is not strong enough to actually lift this block off of the ground. And so I know the weight, it's 15 kilograms, and so the weight is going to be 147 newtons. Well, 147 newtons is bigger than 40, so the weight is stronger than the force pulling up. And actually, we'd want the vertical component of the force, because that's what's going to be opposing gravity, and that's going to be even less than 40. So we know there's no way that this force is going to be able to lift this block off of the floor or the table or whatever it is. Now, what would happen if it did lift the block off of the table? Well, the normal force would go away because the normal force is supplied by the surface. And so if this force was enough to lift this off the ground, then you would just have a vertical acceleration. It's that simple. But since this is not going to be lifted off the ground vertically, we know that this 40-degree force is only going to cause it to slide to the right. Now, it is possible that the x component of this force is not big enough to overcome the static friction, but since we're given in the problem that the block is accelerating, I think we can safely assume that that's not going to be the case. So here I have my force diagram. I've got all the forces, and so I've got my 40 Newton force, and I've got that labeled as FA for the applied force, and I've got my normal force, I've got my weight, mg, I've got my friction force. I've drawn my coordinate system. That tells me which values are positive and which values are negative. And in this little inset up here, I've taken this applied force and I've mentioned that it's going to be broken down into some x and y components. And so I have all my forces. Everything is broken down into x and y directions, and I can just plug in some numbers. Now, we're given that the force, I want to consider this force of the x direction, and really I should label this as FAX, not just FX. But FAX over here, that's going to be 40 newtons, that's the magnitude of the total force, times the cosine of the angle, because the angle is here, this is the adjacent side to the angle, so that goes with cosine, and that works out to be 20 newtons. The y component of the applied force is 40 newtons times the sine of 60 degrees. Again, that's going to be the opposite side of the triangle, so that goes with sine. That works out to be 34.6 newtons. And then the weight, as we said previously, that's 147 newtons. So what do? We break our forces into x and y directions, and we do the sum of the forces equals ma. Now, in this case, we have the y forces, which includes the normal force, the vertical component of the applied force, and then the weight, which was in the negative direction. So I've kind of drawn in a bit of the picture here just to remind you, we had the vertical forces, the weight going down, we had the normal force pointing up, we had the applied force at that angle, which we broke into x and y components, and of course we'll also have the friction force, which is in the opposite direction of the motion, but the vertical parts are going to be the normal force, the weight, and the vertical part of the applied force, and that's what we have here. And obviously the vertical part of the applied force and the normal force are pointing up, so they're positive. the weight is pointing down, so it's negative, and they're equal to 0. Now, actually, I should really write that they're equal to ma sub y, but a sub y is going to be 0. We've already said that this block is not going to lift off the floor. There's no motion in the y direction at all. That's how I know that that is going to be the sum of the forces equal to 0. So if I move these guys over to the other side of the equation, I'm going to solve for the normal force. I get that the normal force is equal to mg minus the applied vertical force, and I can plug in some numbers, and I get that the normal force is 112 newtons. Okay, so that's one of the forces that I need. Now let me just pause for a moment here. I want to talk about a general approach to these friction problems. Notice that you have the normal force being in the vertical direction and the friction force is in the horizontal direction. So they're always going to be perpendicular. The friction is always parallel to the surface that's sliding, and the normal force is always going to be perpendicular. So parallel, perpendicular, the normal force and the friction force are always going to be at a right angle. So when you draw your coordinate system, you're generally going to line one axis up with the normal force and one axis with the friction. And so you'll do the sum of the forces in one direction and solve for the normal force. That's what we just did. The normal force lined up with the y direction, so we did the sum of the forces in the y direction and we solved for the normal force. That's step one. The next thing that we're going to typically do is we're going to use the formula F equals mu F sub n. And that's going to give us the friction force, which will be applied by using the sum of the forces in the x direction, or the sum of the forces in the opposite direction. So we can see doing that here. We have the sum of the forces in the x direction. Again, we have our block, which has a force like that with a horizontal component. This would be my FAX. And then I had my friction force in the opposite direction. And so those are the only horizontal forces that we had in our diagram. The friction force is in the negative direction, so that's why this guy's negative. The applied force has an x component. It's in the positive direction. And the sum of the forces is equal to m times a sub x, where that's the x component of the acceleration. Now, what did I just say? This friction force, that's mu times the normal force. And since this guy is sliding, we're given in the problem that it's sliding, we're going to use the mu sub k, not the mu sub s. If it was sitting there, if it wasn't moving, we'd use the mu sub s. But since it's sliding, we use the mu sub k. Now, we have numbers for everything but a, so we can now plug in all the numbers, and when we solve for a, we get 0.21 meters per second squared, and that's the answer. That's how you work this problem. Let's look at another example. Here we have a 5 kilogram block. It's sliding on the ground with an initial velocity of 4 meters per second. If the coefficient of friction is mu sub k equals to 0.2, and again this k is for the sliding, how far will it slide before coming to a stop? So I have my diagram here. I've got my normal force and my weight. Those are the forces in the y direction. I have my friction force in the x direction, actually the negative x direction. And then I have my initial velocity vector. Now, I've put a little note here. This is a velocity. It's how fast the thing is going. It's not a force. This is a force. This is a force. This is a force. It's a push or a pull. Those are what forces are. So when I do the sum of the forces, I'm not going to include this v in it because it's not a force. I only include forces. I drew the v in my picture because I wanted to know which way it was going, because that tells me how to draw my friction force. I know the friction force is always opposite the motion. So again, what's our procedure? We're going to do the sum of the forces in the y direction, and we're going to solve for the normal force. Then we're going to use our friction formula to solve for little f, and then we're going to do the sum of the forces in the x direction, plugging in the value for little f and solving for a. Once we have a, that's the keys to the kingdom. we can use any of those kinematics equations we know to find out anything we need to know about the motion. How far it goes, how fast it's going, how long it takes to get there, because what we're going to end up with is an acceleration that's constant. How do I know that? Because all of these forces are constant. And so the acceleration is going to have to be constant. And when you have a constant acceleration, you have kinematics equations. So let's do this. The sum of the forces in the y direction, positive Fn, negative mg, equals to ma. And so that's a sub y is equal to 0. It's not leaping off the ground. And that tells us that the normal force is just equal to the weight mg. We can plug in numbers, and we have the normal force is 49 newtons. Now we can use the F equals mu sub k times the normal force equation, and we can use the sum of the forces in the x direction. Those two things together, we'll use those to find the acceleration. So here's what we've got. I've got the sum of the forces in the x direction, and there was only one, the friction, which was in the negative direction. That's equal to ma sub x. So that tells me, solving for a, that the acceleration in the x direction is minus the friction force divided by the mass. And using my definition of friction, I can plug that into there, and I'm left with an acceleration of minus 1.96 meters per second squared. Now, what does that tell me? I've got this object, it's moving with some initial velocity like that. The friction force is like that. In the opposite direction, of course, my coordinate system is in a positive going to the right. This minus sign here tells me that the acceleration is going to go to the left. And what does that mean when the acceleration is in the opposite direction of the velocity? If you remember, that means it's slowing down. So that's what the information tells you, is that this is accelerating in the negative direction, and since the velocity is in the positive direction, it's going to be slowing down. Eventually, it's going to slow down until it stops. Now, as I said, we want to use the kinematics equations to solve for how far it goes, and we can use the third kinematics equation. That's this one here. The final velocity squared equals the initial velocity squared plus 2a delta x. And of course, what we're trying to solve for in the problem is delta x. So if we do a little bit of algebra, we can solve for delta x. We plug in the numbers. We know the final velocity is 0. The initial velocity was given to be 4. And we're going to square that. We're going to divide by 2 times 9.16. And that works out to be 4.1 meters. And that's how far it goes before it stops, which is, of course, what the problem was asking for. Now, this is a fun example. It's kind of complicated, but there's a lot of really good physics in here. And if you really understand this example, you understand a lot about what this material is trying to get across. Okay, so what do we have? A 10-kilogram block is pressed against a wall by an external force making an angle of 30 degrees with respect to the horizontal as shown. So I've got this block, and I am pushing it against the wall, and this force here has an upward component and a horizontal component. And so the horizontal component of this applied force is pushing it into the wall, and the friction between the wall and the block is keeping the block from sliding along the wall. And so the horizontal component is going to press it into the wall is going to push back with a normal force. You're going to have the weight pulling down, and then the friction is going to act to keep it from sliding down the wall. So that's what the problem is. That's the core of what's going on in this problem. Now let's look at what the problem's actually asking. It says, if the coefficient of static friction, that means it's not moving, it's stationary. So if the coefficient of static friction between the block and the wall is 0.35, for what range of forces will the block remain stationary against the wall? i.e., that means, in other words, what is the minimum and the maximum force that will hold the block stationary? So what does that mean? Okay, here's the deal. This applied force is going to have an X component pushing it into the wall and a Y component pushing it up. If the Y component is too small, this block is going to slide down. Now, too small, we've got the Y component of the applied force, we've got the friction, which is pointing either up or down, and then we have the weight. And so this force, if it's too small, the weight is going to make this guy slide down. On the other hand, if I push really, really hard, this component gets really big, and I might actually push it up the wall. And so then the friction would be in the opposite direction, but it would still slide up the wall. So there's a range of forces between those two cases. If I push with not enough force, it'll slide down. If I push too hard, it'll slide up. And so those are the two cases. Any forces in between those ranges will enable the wall to hold the block fast. Okay, so I've drawn my picture here. I've got my XY coordinate system. I've got my weight, which is pulling down. I've got my normal force, and I've got my applied force. And I've broken my applied force into X and Y components here. We've already seen this picture in the previous slide, but I just wanted to sketch for us to be able to look at. Now, we're going to take the first case where we're not pushing hard enough so the block slides down. What that means is that if the block is going to slide down, the friction is going to point up along the surface of the wall. And so now we can do the sum of the forces in the X direction, and this is X component is just FAX. And so the sum of the forces in the X direction are going to be positive FAX, and then of course you're going to have the negative FN, and that's exactly what we put here. FAX minus FN equals MA, and of course MA is 0 in this case, and this would be MA sub X. Why is it 0? It's pressed against the wall. We're not moving it. And so what we can do is we can solve this guy for the normal force, and we get that the normal force is equal to the X component of the applied force. Now we can do the sum of the forces in the Y direction, and let's look at which ones we have. We've got the vertical component of the applied force, and that would be FAY, and we have the friction, and both of those are pointing in the positive direction, and then we have the weight, which is pointing in the negative direction. So we've got FAY plus F minus mg equals 0. Again, that's technically a MA sub y, but that's going to end up being 0. And what do we always do? We plug in for the friction using our relationship that the friction is mu sub k times the normal force. And do you see what my mistake in my equation is? Oops, sorry about that. That should be U sub S because we're talking about static friction. Sorry for the typo. Anyway, we've got the vertical component of the applied force, FAY. We've got the friction, mu sub S times the normal force, minus the weight equals to 0. And that will let us solve for the normal force. So we're going to use this equation is what we had before. We're going to plug in that this guy here, that's the friction force, and we know that this is going to be equal to FAX, so we can just plug that in, and we get that FAY plus mu sub k FAX minus mg is equal to 0. Now, here's the last trick. We know in the picture that this force was given at a 30-degree angle. And so if I have FAX and I have FAY, we know that the opposite over the adjacent is equal to the tangent of the angle, and we were told that the angle is 30 degrees. So I can relate FAY over FAX equal to the tangent of 30 degrees. I can plug that in, and I get that FAY is equal to 0.5774 FAX. That comes for solving this guy for FAY and plugging it in there. And so what I end up with, and I can take this mg and move it over here so that it's positive, and now I can solve this whole equation here for FAX, and I get that FAX is equal to 106 newtons, and that's also equal to the normal force. Now that we have FAX, we can plug it into there and solve for FAY, which we know is FAX times the tangent of 30, and that gives us the vertical component of our applied force is 61.2 newtons. Now we have both the X and Y components of the applied force. We can put them together with the Pythagorean theorem, and that gives us that the applied force is equal to 122 newtons. So that is the force that is necessary to keep the box from sliding downward. Remember, this was the case when the box was going to slide downward and the friction was upward. And so if you apply less than 122 newtons, this box is going to slide down. But as long as you have 122 newtons or better, it's not going to slide down. The friction will be strong enough to hold it in place. Now we can do the exact same thing with the idea that the block is going to slide upwards. If the block slides upwards, then the friction is going to point downward. So we're going to do everything that we just did exactly the same, but where in the previous part of the problem the friction was in the positive direction, now it's in the negative direction. So looking at this, we can do the sum of the forces in the x direction, and just like before, we're going to get that the horizontal part of the applied force equals the normal force. I'm not going to go through this again because it's exactly what we did in the previous part. But in the sum of the forces in the y direction, the one thing that's different is that the friction is now in the negative direction. And so we can again solve for the normal force, knowing that the horizontal component of the applied force is equal to the normal force. We can plug that into there, and we can again use this relationship for the tangent of 30. And what we end up with is that the x component of the applied force is 427 newtons. Now we can use our relationship that we had previously to solve for the vertical component of the applied force, and we get that that's 247 newtons, just times the tangent of 30. Again, we can use the Pythagorean theorem, and we get that the applied force is 493 newtons. And so that is the maximum force that you can apply and still have the block be stationary. If you apply any more than that, you'll be exerting more force than the static friction can hold, and the block will slide upwards. So the answer to our question is that the range of forces for which the block will stay pressed against the wall without sliding either up or down is 122 newtons to 493 newtons. So any force that's greater than 122 newtons but less than 493 newtons is going to hold the block stuck to the wall. It won't slide at all. Now in this example, we're going to revisit our old friend, the inclined plane, but now we're going to put in friction. So this example is about finding what's called the limiting angle of repose. Now repose is a fancy word which just means rest. So here's the idea. A block of mass m is at rest at the top of an inclined plane. The coefficient of static friction between the block and the inclined plane is given by some mu sub s. The angle that the inclined plane makes with the horizontal is slowly increased until static friction is overcome. In other words, we've got this block, and so we're moving it up, we're increasing the angle, and as the block is elevated to a higher angle, the component of gravity pulling it down the plane increases. And so this force is going to slowly increase until the block starts to slide. And the problem is to find where is the angle where the block first starts to move. Determine the angle at which the block moves. And this particular angle is called the limiting angle of repose, because any angle bigger than that, the block's not going to be able to stay at rest anymore. It's going to start sliding down the inclined plane. So here is the picture of the inclined plane that we have drawn. Now, when I drew this inclined plane previously, I had labeled the components of the weight, and I drew them like a triangle. But in this case, I've actually drawn them more parallelogram style. And I like drawing it this way because you can really see that the component of the weight down the inclined plane is what's pushing it down the plane. And of course, that's mg sine of theta. If this angle here is theta, we know this angle here is theta. So this guy is going to be the opposite side. And I've just moved it up to make it look pretty. But we have the mg sine of theta is pulling it down the plane. The mg cosine of theta is pulling it into the plane. And of course, we're also going to have the normal force, which is perpendicular to the plane. I've got my coordinate system here, and all that's exactly like we had before. I've only shifted this arrow up to the top here. What's new is the friction force. And we know that the friction force is going to be along the plane opposite the motion. And so that's going to be in the negative x direction. So what I want to do is I want to do the sum of the forces in the x direction and the sum of the forces in the y direction. If I do the sum of the forces in the y direction, that's just going to be Fn minus mg cosine of theta. That's equal to ma sub y, and that's equal to 0 because it's not leaping off the plane. In fact, the whole part of this problem is that we don't want the block to move. So we know the acceleration is going to be 0. And then we can do the sum of the forces in the x direction, and that's going to be the mg sine of theta minus the friction force, and all of that is equal to ma sub x, and of course that's equal to 0 as well. And that gives us the forces in the x direction. And of course, we know that we're going to need the relationship that F equals to mu sub s times the normal force. So again, whenever you have friction, these are the three things you need. You need the sum of the forces in the x, you need the sum of the forces in the y, and you need the friction relationship between the friction and the normal force, because the sum of the forces in one direction is going to have the friction, the sum of the forces in the other direction is going to have the normal force, and this is, you're going to plug this into one of those two to solve for something. So I've just rewritten these here. For the y direction, we had the normal force minus mg cosine of theta equals to 0. And that tells us that the normal force is equal to mg cosine of theta, just solving for the normal force. Then we can do the sum of the forces in the x direction. And what I've done here is I've plugged in that relationship, that little f is equal to mu sub s times the normal force. So I just plug that in here, and then I can take the normal force, plug it in there, and what I end up with is that mg sine of theta minus mu s mg cosine of theta equals to 0. Sub s. Now the problem is to find the angle. I want to find the angle that this relationship is going to be true. So all I need to do is solve this for theta. Now, if I bring this guy over here, I get mg sine of theta equals mu sub s mg cosine of theta. I can immediately see that the mg's are going to cancel. And if I divide both of these by cosine, the cosine will go away. I'll get sine over cosine over here. Sine divided by cosine is tangent, and I'm left with tangent of theta equals to the mu. And then to get the theta, I just take the arctangent of both sides, and I'm left with this. So whatever the coefficient of friction is, if you take the arctangent of that, that will tell you theta. That's the angle, that's the maximum angle for which the block will remain stationary. If I go beyond theta, the block's going to start to slide down. And by the way, this is a way that you can actually measure the coefficient of static friction. You can build an inclined plane, put your two surfaces on it, and increase the angle of the inclined plane, find the angle when the block just starts to slide down, and then you can use these relationships to solve for the coefficient of static friction. And those are some problems that hopefully give you the idea of this approach for solving friction problems.